In this video, we're going to continue looking at area and volume using polar double integrals, and we're specifically going to focus on volume in this video here. So in our first example, we're going to set up a polar double integral for the volume under z equal 9 minus x squared minus y squared. And in these problems where it says find the volume under a surface, it's implied that you actually want the volume between the surface and the xy plane. So let's see if we can draw a picture. This surface here is actually a paraboloid. Remember that if you just said z equal x squared plus y squared, that's a bowl that's opening upwards. Now what we've got is z equal 9 minus x squared minus y squared. So the negative signs actually flip this bowl upside down, and then it's been lifted up 9 units. So it looks something like that. So we want to find the volume under this paraboloid and above the xy plane. So just find this enclosed volume here. All right, so to do that, we need to have an understanding of the region R in the xy plane. So the region R that is forming the base of this volume. So let's shade that in a different color. Let's shade it in maybe in blue. So there's our region R. One way to visualize that region is imagine you're sitting up here at a very high Z value and just looking down on your surface. Imagine what sort of shadow you would see cast by the volume there. So you could say that the region R here is the projection of the volume onto the xy plane if that projection is just done vertically. So to think about our region R, what we're actually going to do is we're going to think about the intersection of the paraboloid with the xy plane. So we're going to say z equals z. Formula for the paraboloid is z equal 9 minus x squared minus y squared. And formula for the xy plane is z equals 0. So by setting z equals z, what we're finding is the projection of that volume onto the xy plane. Right, now we're going to be doing this in polar coordinates. So if we think of this as 9 minus r squared, that's going to be pretty helpful. 9 minus r squared equals 0. In other words, 9 equals r squared. We could say r is either plus or minus 3, but in the context of polar coordinates, r is always positive, or at least non-negative. So r equals 3 is the radius that we're looking for. And that way we can give a more specific description of this region R that we're seeing in our picture. It's a disk, and we figured out the radius of that disk. So we can now give the complete description of what that region R looks like. Radius values are going to range between 0 and 3, and theta values are going to range between 0 and 2 pi. So if we look at this region R just in the xy plane, it's just a disk of radius 3. You could say it's a circle of radius 3 and then just filled in. So to describe that region in polar coordinates, we're just imagining taking these little rays that radiate out from the origin. The R values we're capturing everything from 0 to 3, and the angles that we're capturing, well, 0 to 2 pi because we're going all the way around that disk. So now that we've got a description of our region, we should be able to set up our double integral that's going to represent the volume. So the general formula is that the volume under a surface is going to be the double integral over the appropriate region of z times dA. If we're in polar coordinates, dA is going to be r dr d theta. And the z just comes from the formula for whatever surface we're working with. In this problem, it was the paraboloid. Z was 9 minus x squared minus y squared. And since we're doing this in polar coordinates, we can rephrase that as 9 minus r squared. So that means we're doing the double integral over our region R of 9 minus r squared times r dr d theta. And in our next step, we'll put our limits of integration on there. So if you want, you can multiply the r through with the 9 minus r squared. You could have 9r minus r cubed for our integrand. If we were actually going to go ahead with the integration, we would certainly want to do that so that we're ready to integrate. If you're just setting up the integral, I would say it doesn't matter whether you keep the integrand factored or whether you expand it out. But certainly we need to put our limits of integration on there. So we said up here that our radius values were going from 0 to 3, and our angles theta were going from 0 to 2 pi. So we have successfully set up the double integral in polar coordinates that gives the volume under that paraboloid. So let's find the volume of the ice cream cone bounded by the following two surfaces, z equal root x squared plus y squared, and x squared plus y squared plus z squared equal 4. Well, why don't we start by trying to sketch these two surfaces. So z equal root x squared plus y squared is a cone, opening upwards like that, vertex at the origin. And then our second surface here, x squared plus y squared plus z squared equal 4, that is a sphere of radius 2. So we're looking for this volume here that's sitting between our cone and our sphere. So just trying to find the volume of that three-dimensional region there. All right, now we're going to need to understand what points in the xy plane we need to integrate over. So let's imagine taking that three-dimensional volume, which looks like this. Imagine that our xy plane is sitting down here. And we're going to just try projecting all these points in this region, just project them vertically onto the xy plane. So you would get a region that looks something like that. So geometrically, what you could imagine, you could even imagine shining a flashlight straight down like this, and you'd just be asking, where's the shadow of this volume falling in the xy plane? So that entire shadow in the xy plane, that's the region R that we want to be integrating over. So another way to visualize this region R is it's the set of x, y coordinates that are captured at the widest point of this volume, and that happens at the point where the two surfaces intersect. So if we were to set z equal to z, that would be a good way in general of figuring out the region R. In this case, it might be a little tricky to set z equal to z because we'd have to actually solve for z in that second equation. So a slicker way to do it in this particular situation is to say z squared equals z squared. But I would say in general, think about setting z equal to z as usually your go-to procedure. So this is a bit of a special case. Well, the first surface, the cone, has equation z equal root x squared plus y squared. So if we square z, we would get x squared plus y squared. And on the other hand, the second surface here, the sphere, if we solve for z squared in that equation, we'd have 4 minus x squared minus y squared. Okay, now polar coordinates are going to be a good choice here because the region R is actually a disk. So whenever you have a circular object like a disk coming up in your problem, polar coordinates are typically going to make things a lot easier than xy coordinates. All right, so if we move into polar, we'd have r squared equals 4 minus r squared. In other words, 2r squared equals 4, which means r squared equals 2. So r could be either plus or minus root 2. But in polar coordinates, our radius is never going to be negative, so we'd immediately say r equal root 2. What that's giving us is the radius of the disk that we can see in our picture. So now we can write down a complete description of our region R. If it's a disk, then we're capturing all the radius values between 0 and root 2, and we're capturing all the angles between 0 and 2 pi. So once we've got our description of R, we can think in general about how to set up a double integral for the volume between two surfaces. So it's going to be the double integral over R. We're going to go z top minus z bottom times dA. So I'm going to draw another picture of our ice cream cone just beside this formula, and we'll see if we can figure out the formulas for z top and z bottom. Okay, so z bottom is coming from the cone. We know the equation of the cone was given in the question as root x squared plus y squared. If we write that in polar, it would just be r. And z top, x squared plus y squared plus z squared equal 4. We could say z squared equal 4 minus x squared minus y squared. Taking roots, z equal plus or minus the square root of 4 minus x squared minus y squared. The positive root gives us the upper hemisphere and the negative root gives us the lower hemisphere. So we're going to choose the positive root here because we're talking about the upper hemisphere of that. And then just putting that into polar, this is going to be z top, and it is the square root of 4 minus r squared once we get that into polar. So I'm going to highlight our formulas for z top and z bottom, and then I think we're ready to continue with our integration. All right, so we got the double integral over r. We've said that z top is going to be root 4 minus r squared. We're subtracting off z bottom, which is r, and if we're in polar coordinates, dA is r dr d theta. At the same time, we could put our limits of integration on here. So those are coming from our region R, which we've got described up at the top of the screen here. So our radius values are going from 0 to root 2. Those are going to go on the inside integral. And then theta values going on the outside integral. Those are 0 to 2 pi. So if the problem was just to set up the volume, then we would be done. But we're actually going to do the computation here and just practice the computation of polar double integrals. So first thing I would do is just multiply the r through the integrand before thinking about doing any integration. So we'd be integrating r times the root 4 minus r squared, and then that would be minus r squared. That's going to get integrated with respect to r and then with respect to theta. So if we look at this first term here, this guy here is going to require substitution to get integrated in terms of r. So I would consider doing the substitution just over on the side and then coming back to the main problem of evaluating this double integral once we've got that substitution figured out. So let's just create a box here and we'll do a little bit of side work. All right, so the problem is to integrate with respect to r, something that looks like r times root 4 minus r squared. Let's just consider this to be an indefinite integral for the purpose of doing the substitution. So what we're going to sub is u equal 4 minus r squared. That's going to make du equal to minus 2r dr. And that means that minus 1/2 du is the same thing as r dr. Okay, so that means we can rewrite our integral in the language of u. See, the r dr is going to be minus 1/2 of du, and the root becomes a root u. All right. So in terms of getting this integrated, then we're going to have minus 1/2 times, well, we're going to do the integral of root u, which is going to be u to the 3/2 times 2/3. And since we're just treating this as an indefinite integral, I'm going to write plus c just because it's good form to write that. So we'd end up with minus 1/3, and then we'd have u to the 3/2 where u was 4 minus r squared. So that gives us the integration of that first term there with respect to r. So now that we've got that figured out, I would say we could come back to this step here and just continue our double integration from there and get this evaluated. So picking up where we left off, we have the integral from 0 to 2 pi. I'm going to write the d theta at the back. And we're actually going to do the inner integral here. Let's integrate with respect to r. We know the first term would come out to minus 1/3, 4 minus r squared, to the power 3/2. So we know that thanks to our substitution. And if we then integrate minus r squared with respect to r, we'd have minus r cubed over 3. Okay, so this entire expression has to get evaluated at r equal √2 and then r equals 0 before we can do the integration with respect to theta. So let's spend a little bit of time here doing the evaluation. We'll keep the integral on there, we'll keep the d theta on there, and we'll just work on evaluating right now. So first subbing in r equal √2. Okay, well, if we look at this bracket here, if we square √2, we're going to have 2. So in other words, we've got minus 1/3 times 2 to the 3/2 minus √2 cubed over 3. Okay, and then we still need to subtract off the value at 0. So subtracting off the value at 0, we're subtracting off a negative term, so that's going to be a positive 1/3 times 4 to the 3/2, and then the second term that we're subtracting off is 0, so I'm not going to worry about writing that down. Okay, so we're getting this expression here. Let's clean this up a little bit. So 2 to the 3/2, you could think of that as 2√2 if you want, and you could call this whole term here minus 2√2 over 3. The second term is actually the exact same thing. It's another minus 2√2 over 3. And then this last term, 4 to the 3/2, is 8. So we could call that a plus 8/3. All right, so in other words, is integral from 0 to 2 pi of 8 minus 4√2 over 3 d theta. Now notice that there's no theta in this integrand. So this is just like integrating a constant. And when you do that, you're just getting that constant times theta, and then that theta is getting evaluated at 2 pi and then at 0. That's going to give you 8 minus 4√2 over 3 times 2 pi. And let's write that a little more nicely. We can factor out the pi and make that 16 minus 8√2 pi all over 3.